Hi everybody. Well, today we have lecture 10. In lecture 10, we will discuss the address mode. And so I'm pretty sure as most of you already are familiar with address mode. But we're quite familiar with it. But however, we didn't study all details. So in this lecture, we study all the details of the different address mode. So we will have an overview about address mode. So we will talk about the effective address first. Then we go to address mode. Then we go to see the individual listed the address mode for the 68H12. And I will also show you some examples of the different address mode. So we can become more familiar about the different address mode of the 68H12. Of course, we focus on the 68HC12 address mode. So when we go to a different microcomputer, okay, so it may have its own different address mode. So at the beginning, let's talk about the data access and the address. Okay, in general, okay, we're determining how the instructions can access data from memory. Okay, is a very important issue in design of microprocessor. Okay, because that really affects the performance of microcomputer system. Okay, yes. So if the data that we need for an instruction is in memory, then what the microprocessor will form a memory address to access the data from memory. Okay, however, if the data we need is already in the register, okay, if the data we need is in the register inside the microprocessor, then we don't need a memory address because the data is already in register or is already in a particular register of CPU. Then what? Probably we need name a register, okay, or we even don't need name a register. But anyway, the memory address is not required or is not needed. So the different instructions, okay, they have different ways to access data. So this is where we come to the so-called effective address. So what's the effective address? As I mentioned to you before, effective address is the address formed by the microprocessor as the part of instruction execution. So that's where the real data, okay, is not address. That's where the real data we need for instruction locate. So effective address of an instruction is the actual location. The actual location here, actual location of data, not the address. Okay. So the microprocessor uses effective address to control the memory, to access a memory. Okay. So there are different ways we can form effective address for data. Even the different instructions, okay, they can tell microprocessor to form effective address in different ways. In other words, what? The different instructions of the 68H12, it has its own way to form address. Okay, so those different ways to form an effective address to get data for an instruction is called address mode. So we have effective address. That's where our real data locate. Okay, so the different instructions, okay, they form effective address in different ways. Those different ways to form the address, to form effective address, is called address mode. So we simply say address mode is a particular way that the microprocessor forms effective address for an instruction to acquire data, which is necessary for an instruction. Now, as I mentioned before, for the 688012 microcontroller we study, there are 6 different address modes available. Or we simply say for the almost the 300 different instructions of the 688012, we have 6 different address modes. There are 6 different ways for all of these almost 300 instructions, okay, to form an effective address. So they are all here. There are 6 different ways. Okay, well, some of this word, and I think we already covered it before. So these 6 different address mode are inherent address mode, okay, immediate address mode, the direct address mode, extended address mode, index address mode, and the relative address mode. Okay, and in today's lecture, we'll try to finish the first 4. So we try to finish the first 4 right here. Those first 4, we try to finish this 4 in today's lecture. Then for the rest of 2, they're a little bit more complicated. We'll try to finish in next lecture. And as I'm pretty sure some of you are already very familiar with some of address mode because we had an overview of them. But before we get to the details of each of individual address mode, let me comment on this. Now, in comparison, for all of this inherent address mode, immediate, direct, extended, index, and relative, and all of these address mode, they're quite different, except these 2. Except these 2. These 2, let me use different mark here. These 2 are quite similar. The direct address mode and extended address mode, they are quite similar. Okay, because the way we form address, the way we get data, okay, they're pretty much the same. With the only difference is about what? Is about the address. For the direct address mode, okay, we provide address to get data from memory. So we provide the address of memory location from where we get data for the instruction. Same thing for extended address mode. We also provide address of memory location, okay, to get data for the instruction. The only difference is what? For the direct address mode, we only provide 1 byte address. In other words, what? Okay, even though a full address of memory location is 16 bits, but for the direct address mode, we only provide what? Low odd byte address, only low odd byte. Low byte, or is 8 bits. For the extended mode, we need to provide all 16-bit address. Or we call it full address. Okay. Now, even for the same location, assume like a 00AP. 00AP is full address. Okay. Now, if you try to present this address, okay, that the memory location whose address is 00AP in hexadecimal, then For the direct address mode, we only need to provide AB. For the extended address mode, we need to provide 00AB. Although the actual location are the same. But in comparison, for direct address mode, we only provide a low byte address, only 1 byte, which is AB. But for extended mode, we need to provide 00AB, which is 16 bits. All others are the same. Of course, extended address mode because we have more address. Okay, so and CPU can access only 1 byte at a time. So CPU have to access what? The both byte of address for memory after before executing. So CPU have to fetch the address for both bytes. So for extended address mode in general, it requires more fetch of CPU. So that requires a little bit more. It requires more time cycles to process it. All others, they're quite different. Inherent address mode is quite different from immediate address mode. Immediate address mode is quite different from direct and extended. And index are also quite different. Relative address mode is also quite different. So only two are they're quite close is the direct mode and the extended mode. So let's go to discuss each of this address mode. So let's start from first one, inherent address mode. Okay, so as I mentioned before, for the inherent address mode, the instructions, okay, they need data, okay, inside the CPU registers, either inside the CPU registers or they don't need any data outside of CPU. Or in other words, they never touch memory. They never deal with memory. Any data required for the instruction already inside the CPU, already inside the CPU registers. So these instructions already have data inherently built or built inherently. So the instructions that use this address mode either have no operand, we only have opcode. So they either have no operand, or all the needed operands are inside the CPU registers. So either we don't need any operands, or the old operands of data already inside the CPU registers. But in either case, no matter we have operands or not, or they are inside the CPU registers, in either case, CPU does not need to access any location of memory in order to complete the instruction. So as I showed you before, so the way we can easily identify this type of address mode is to check to see if the instruction has operand or not. So if the instruction has no operand, like those, only have opcode, then this instruction runs in the inherent address mode. So the opcode contains all the information, all the needed the information. Here I simply show you three of instructions that runs in inherent address mode. ABA. Okay, I remember and I mentioned ABA when we discussed the addition, right? Yes, back to early. So ABA is to add the contents of accumulated B to accumulated A and leave the result in A. Okay, so this instruction already very clearly or explicitly tells the CPU, okay, what data I need to process, where it comes from, where to store it. So here ABA is already add here. This A means add here. This A means add. Then B means accumulate B. A means accumulated, we leave in A. So we add the data in accumulated B to accumulated A, and leave a result in accumulated A. So no data needed from memory. Okay, so that's why we only have one field, which is opcode field. Remember, we have 4 fields for any instruction. Here we only have one field, which is opcode. So we don't need any operand field. Here, nothing. Same idea for no op. This no op is not very commonly used. So mainly it simply said what this instruction has no operand, no operation. So it does not have operand at all. So NOP, it means no operation, does not do anything. So when we move forward, I will show you some examples where we use NOP. So does not do anything, no operation at all. It only cause some time delay. INX, okay, you see, no operand, only the opcode itself. INX means it increments the value of index register X by 1. It's right here. INX is from its name, because those names are the mnemonics. Names already contains a lot of information. INX means increment the value in index register X by 1. Or we can simply say this means what? X plus 1. Right? Yes, X already a CPU register. So here we do not deal with any memory location. All data we need are there, already given. So that one is quite straightforward, because we can check to see if that instruction contains the operand or not. The second mode is immediate address mode. I'm pretty sure we already did some exercise before, and we already used some of the immediate address mode instructions. So for this type of address mode, okay, the data we need for the instruction is given explicitly in the instruction. So a custom data is already given in the instruction. Now it's called so because the actual data required for the instruction follows immediately the opcode. That's why it's called immediate mode. Immediate mode here. Immediate mode. Why is it called immediate mode? Because data follows immediately. So following the opcode immediately is the operand. In general, this operand is custom data, is given explicitly. Because the data is constant, so in general, as what we learned before, so it should start with pound sign. Pound sign, then whatever following is the data. Data can be in binary, or hexadecimal, or decimal, whatever. So the data value in operand field can be 8-bit long, can be 16 bits long. That depends on the context. Of the instruction. Okay, sometimes if we need to load value in an accumulator, like in an 8-bit accumulator or in an 8-bit register, then our data is 8 bits. But if you try to load the value in a 16-bit register, like a D, then this value should be 16 bits. Or if this value is not 16 bits, it's processed like 16 bits. So because all data is required for the instruction already given in operand field, So we never need to access memory. So this type of instructions do not contain an address. No need to address. Anything following the opcode is data. So as I mentioned, we do need pound sign. So immediate numerical value, which is the operand for the opcode, is always started with pound sign. Always start with pound sign. So we simply say pound sign in operand field indicates this particular address mode. So here I show you two examples. LDAA pound sign $55. So right here we see this value. We see this value $55 is hexadecimal 55 is a numerical value, is a constant data. We need to load this 55 in hexadecimal in A, equivalent A. So this is what I'll show you. So 55 is already a numerical immediate value we can use. So this simply said place value 55 in equivalent A. So this 55 is 1 byte. Okay, which one we can load into A. So after this instruction is run, then what? Assume this is equivalent A, so 55 load in A. Well, next one, LDX. Okay, pound sign, $200. Here, because we try to load a value in the index register X. Okay, so we load 200, this value, which is 2 bytes. Okay, which is 2 bytes. So we try loading A. So if this is the A, here we go. This is A. This X. Excuse me. This X is 2 bytes. 1 byte here. This is 8 bits. This is another 8 bit. So we try to load 2000 to this index register X. So after we load, the value we have is this 2000. So when we try, so as I mentioned before, when we try to load a constant numerical value in X, that makes X points to this address in memory. So here we load 2000 in X. That means what? After this instruction is run, X points to memory. Okay, memory location whose address is 2000. Okay, that's how we initialize an index register X or Y. So then we can use what we can whenever if we want to access our data, we X points to, okay, or a list data, then we can simply use X or X plus 1, X plus 2, like that, as I showed you before. So this is so-called immediate mode. So those two are very straightforward. LDA load 55 into A on 1 byte. LDX, which is load 2000, okay, which is 2 byte at X. Now let me show you one more. LDY pound sign $44. Here you see our destination register is Y. Here I show like a Y. It's 2 bytes. Byte 1, byte high, byte low. It's 2 bytes. but the value we're given to load is only 1 byte. See, so this is only 1 byte. Only 44. Now what happened? Okay, although the value is on only 1 byte, so this value only goes to the low order byte of y. So 44 goes to here, because the value is only given 1 byte. 1 byte always goes to lower, and 1 byte this address on the constant value always goes to low order byte of y. Then what? Okay, high order byte of y will be made 00. So in this case, what we simply say this: we load 0044 in y. Okay, so only 80 bit value was supplied. The assembler will generate a 16-bit value, because you need to fill the index register y. Okay, y requires 2 bytes, because CPU expects a 16-bit value here, as I said. So we're similar to the one I show you here for x. $x $$200. This one makes index register y points to a memory location whose address is 0044. So let me erase all of this. So this try to say, this means what? This means this. So after we do this, if this memory here if this address is 0044, then after we run this, after CPU runs LDY $44, that means what? We make y is here, y points to this location. Or we simply say, if you hope the y points to this location, you have to load this numerical value in y, as we did here. Now, so make sure this is value. So don't forget the pound sign. This is very important. If you forget the pound sign, then address mode is what will be changed. Then the value we load into y may in general or may not be 44 anymore. It will be the data value stored at right here. It's different. That's another different type of address mode, because in this case the 44 is not a constant value. It's address, a memory location, and we need to load the data at this address into y. So that runs in a direct address mode. So that's why in that case, we now come to the direct address mode. So in comparison to the immediate mode, the operand specified here is address of memory location, where the data we need access. But also make sure this address, as I mentioned a moment ago, right here, as I mentioned here, right here, the address is only 1 byte. So only 1 byte address is specified for memory location, and the instruction need deal with data at this location. So our data address is only single byte. Only single byte. So we simply said what? We only specify the least significant byte of effective address for data. That implies, the high order byte address is 00. So we simply said what? So So the address range will be this range from 0000 to 00FF. But when we write a program, we only simply specify low order byte. So the address range will be fall into this range region. So we never go beyond 00FF. So this type of address mode is sometimes called a zero-page address mode. Zero page. Because everything is done, all the address word, it has to fall into the region of from 0000 to 00FF. That's like what everything is what. They never go beyond one page. So all data we can access what is always on this page. So it never go beyond the range of one page. No, but so although this is the whole region, but when we specify in the instruction, we only specify low order byte address. We don't need to specify high order byte address anymore. But for sure, high order byte address is 00. So we don't need to specify this. That implies high order byte address is 0. So let me show you two examples for the direct address mode. The first one, LDAA 20. So this like if you compare this one with the one I show you here, I show here it's quite different. So all over this immediate mode they have pound sign, but this one does not. So immediate following LDAA is a numerical value. This value. This means what? This 20 is address. That means what? Here we try to load a value into A. But the value we load into A is not 20. The value we try to load A is what? Is a data at a memory location whose address is 20. Or we simply write down this way. We try to write down the data value in this memory location whose address is 20. So what's the value? We have no idea. But the value should be 1 byte, because you only load one memory location. Each memory location only contains 1 byte of data. So address only specifies as 1 byte. There's only 1 byte. Now let's check the second example, LDX. It's very similar to the one on top. The only difference we change from is what? Is our destination register changed from A to X. We know X here is 2 bytes, while A here is only 1 byte. So although our destination register is 2 bytes long, here, this is called a high order byte, this is called a low order byte, but the address is only 1 byte. Then when CPU will load automatically the 2 bytes value. They locate what at this address and the following location, which is at 21. So as I mentioned, the high order byte take the value at low address. So the high order byte, this byte, we get the values at 20. Low order byte take high address. Okay, this low order byte value, should come from a location at 21. automatically, although we only specify one address, but because our destination register is 2 bytes, so it will fetch twice, starting from 20 and next one. So after we load, then what? Then after CPU finish this instruction, okay, then what? That we make X points to memory location whose address will be the value stored at the 20 and 21. So although here we fetch 2 bytes, but address is still only 1 byte. That's why we call the direct address mode. Now we come to extended address mode. So as I mentioned, in comparison to the direct address mode, the only difference between them is what? Address specified as 16 bits. The full 16-bit memory address is specified in operand for the extended mode. So in this case, because address can be 16 bits, that can reach to any memory location at the 64 byte of the 68H212 microcontroller. Because you have 16-bit address, so that means what? Let's make the range is what? From 0000 to FFFFF. Totally those are 16 bits. This 16 bits, so total give us 2 to 16. That gives us 65,536 location. That's simply called 64 KB. Each K is 1024. If you multiply 64 by 1024, that's equal to 65,536. So this is very similar to the direct mode. Only difference is what? Address. But the data value load is still same as the direct address mode, because that's memory. The only difference is what? Is address. So same example is very similar to this one, LDA. Here we have 20. But if you have extended mode, like here we have 2000. This means what? We load the value at the memory location 2000 in A. So data value is still 1 byte. This is still 1 byte, but address is 2 bytes. Now, even though, for example, I showed you a moment ago, like the one exercise we did in homework. If you have this, that's also in extended mode. Because here the address here, because this address is 16 bits. So also runs extended mode. Let's take a look at one more. ADDD. Here we try to add a value in accumulator D. We know accumulator D is always 2 bytes. So here I show you accumulator D like this. Accumulator D like this. This is D here, always 2 bytes. But it consists of accumulator A and B. 2 bytes. Here we try to add a value. We try to do addition. Try to add a value to what? To the value we already have in D. So whatever value we have here inside here, we try to load the value there. What's the value? The value we load, the value we need to add to D, locate at memory. But But this value we add to D will be 2 bytes because the value in D already 2 bytes. So we had to load 2 bytes from memory. But here we only specify the first address, which is 1030. So now we need to load the value for memory, memory locations at 1031. At 1030 and 1031. Then we add into the value in D. So in this case, the value we load from 1030, we add into this part. Let me change different marker here. Let me change this one. At this location we add here, and at the 1031 we add into B. Yet I mentioned high order byte take from low address. Low order byte, this low B at right has low order byte take what from high address. So CPU will automatically reload 2 bytes. Okay, which locates at 1030 and 1031. So all of this are addresses. So I think probably that's good time we stop here. And so mainly we discuss effective address and address mode. And then we mentioned about we have 6 different type address mode, and we focus on the first 4 that are inherent address mode, immediate address mode, the direct address mode, and the extended address mode. The next time we will finish the rest of them, and they are a little bit more complicated than those we already covered. So that's pretty much we prepared for lecture 10.